Hello, everyone. Good afternoon. Um, my name is Tony. I'm from Keyfactor. I'm solution engineer for the APJ region. So today, I want to talk about the migration to post-quantum cryptographic, and we will be focusing also on the our open source innovations, and our groundworks that we have done for interoperabilities. So this is the agenda today. We will share a little bit background since there are a lot of people in this room haven't really aware of this problem or this risk. And then we will talk about the migration challenges, what are the strategies and also the framework itself. And then we will dive into Keyfactor interoperability testings, and I will also show some demos using our tools and also other tools, other libraries like OpenSSL and stuff. Right, so the security of cryptographic algorithms is really constantly challenged by the increase in the computing power, right, and also the sophistication of crypto analytics techniques. So we have actually experienced in the past where we migrate other algorithms like TripleDES to AES, SHA-1 to SHA-2, and upgrading from RSA 1000 to 2000, and also now recommended to use the stronger keys like RSA 3000. But when quantum computers are capable enough, it introduces benefits and also risk, right? From the risk perspective, there are two major risks. One is harvest now, decrypt later risk. So the idea is basically adversaries can steal today's encrypted data, and hopefully in the future they can access quantum computers. They can break today's data, decrypt it, and understand the contents, and that's actually happening right now. So adversaries are actively collecting those data, and especially government to government communications and all this stuff. The other perspective is trust now, forge later. So the idea is basically attackers could use the signed data or certificates now, but then forge digital certificates and undermine your trust. So I think previously some of the speakers mentioned about S-bomb signing, right? So that can be a case where what you are signing today, what you're trusting today, can be forged later when we use quantum computers. So the good news is that NIST from the US has standardized a few post-quantum algorithms from digital signing and encryption, and also adding diversities of different algorithms, from different underlying mathematical problems. MLDSA is basically based on module lattice-based algorithms, and also MLChem is using module lattice-based, but using for encryption. They're also adding more algorithms like HQC as a backup if ML is not working or is being break in the future. So that's alternative options to be used, and as well as is quantum safe. And I highlight in the red box is these slides. Actually, last week we have this new MLDSA X509 certificate standardization in the RFC 9881, which give us a more future proofing or standardization from RFC perspective, and give more convincing about the migration. So yeah, it's good news. I also have this slide about the migration timelines from different leading countries and institutes. So the consensus is basically we need to migrate fully by 2035, and the legacy algorithms like RSA and ECC will be likely deprecated by 2030. So if we count from today, it's like 5 years to go. In local contexts in Korea, there are also publications of PQC transition master plans, and leading by National Intelligence Services and KISA, who is Korea Internet and Security Agencies. And also there are quite a few local PQC algorithms. They are not in the list of NIST approved, but this is can be used as a local cryptographic algorithms to be used in the local context. Yeah, so HITAG with the digital signing algorithms, and SMAUGT, SMACT is encryption. So they're the winner of KPQC. So if we talk about the migrations for PQC, what are the challenges? So there are actually 4 major challenges. There are many more actually, but these are the major 4 challenges. Number 1 is, of course, the complexity of migration. Basically, we have all this cryptography in the operating system. So I was talking to SUS, Debian, all these operating system, they have a lot of libraries, cryptography underneath, how we can migrate those systems into quantum safe OS. There are actually many more algorithms and cryptographics in organizations' environment, in the cloud, in the applications, certificates, PKIs. All these are in the organization, but unfortunately, we don't really have very good visibilities on all these data. And we also don't know what those data are protecting, especially those critical infrastructures and data. So that's the number 1 challenges. The second one is interoperability. So even you put a PQC algorithms or PQC certificates in your applications or keys, it doesn't give you the assurance it will work, right? So we need to do a lot of end-to-end testings, making sure the dependencies are all addressed, all the clients and can talk to the servers, can make sure the ciphers and can be agreed, and all these stuffs need to spend a lot of time to do the end-to-end testing verification. And number 3 is transition vulnerability. So likely the transition or the migration will take a few years. So how can we ensure, some of the systems are migrate to quantum safe algorithms, some are not? How can we make sure, we can monitor those systems, monitors those vulnerabilities, and ensure the compliance for critical systems? And lack of agility, which is the last one, is how can we do this in scale, right? How can we automate all these keys, cryptographics into systems automatically, right? Without making this PQC migration very costly and risky and disruptive. So PKI, public key infrastructure is of course using legacy algorithms, RSA and ECC. Of course, that's a big task for us to migrate PKI to a quantum safe PKI. So there are a few approaches. Number 1 is a complete migration. So it's basically you switch directly from legacy keys to a quantum safe keys and quantum safe PKI. It doesn't make sense to a lot of organizations, but it does make sense for especially in the manufacturing industry, because once you ship the devices or ship the, for example, vehicles, IoT devices, it's very hard to change or switch the algorithms. So making a complete change is one of the strategy. For most of the enterprise organizations, maybe transitional is a better approach. That's where you're running both a legacy PKI and the post-quantum or quantum-safe PKI at the same time, and slowly phase out the legacy systems and using the quantum-safe PKI. There are also some draft standards using hybrid PKI. Basically, it is PKI or certificate format that has two keys or two certificates or two signatures in it. So using that to be able to compatible with legacy system and new system is one of the other strategy. But today we're not going into the details of hybrid certificate. So if I put into a framework of how we can manage, how we can do this migration process, there are 6 major steps. Number 1 is to prepare to have the full visibility of all your cryptographic assets in your operating system, in your libraries, applications, key stores, everywhere. Understand where they are, what they're protecting, and also identify those legacy systems that will never be able to migrate to PQC because some of the mainframe, some of the banking system, they're very legacy, they're incapable to migrate. How can we build the defense around them to protect those critical assets? That's also a different perspective. So number 2 is, I think I mentioned number 2, but on top of that, we need to also put a risk assessment tools on top of all these crypto assets, understand what's our priority, so we can action on those top priority crypto assets. And the third phase is to implement, so we can start building quantum safe cryptographic PKIs, issue quantum safe certificates, put in your servers, put in your Apache, for example, do some signings using SBOM signings, understand what's the impact and all this, do more testings and understand the dependencies and all this. And the fourth phase is to build crypto agile. This, of course, is to prepare number 5, be able to automate a massive scale of migration, all the keys, certificates, root of trust, and using a platform. And also we want to monitor, continuous monitoring, making sure we are staying compliant and also ensure that the security perspective. This is a Keyfactor platform, but we will be focusing on the middle box, which is also available in a community edition. So EJBCA is our PKI platform. Bouncy Castle, of course, is some of you might know is cryptographic API library, and sign server is for signing. And we will talk about interoperability using those tools. So what we're focusing on, what we can manage, right? So all the PKIs, certificates for TLS, MTLS, encryption, key exchange, and signing verification perspective, and also CLM, which is a lifecycle management of certificates and protocols. We are actively participating in industry hackathons, for example, IETF, PQC hackathons, SAVP testings, and actively testing against other libraries, for example, OpenSSL, CryptoLib, and others. So this is what we have done so far, all the groundworks that we have done using our tools. So EJBCA, we have tested certificate issuance and issue MLDSA and other certificates using different algorithms, and also cross-validate using OpenSSL. Session encryption and authentications, we have done MLCAM for encryption, MLDSA for authentication, and cross-check using OpenSSL or Bouncy Castle. This is for signing, right? This is also very important when we talk about supply chain security. So we have used MLDSA, SLHDSA for signing using sign server, and also verified using different libraries. Encryption, MLCAM, timestamping, this is still in progress, and we're just waiting for OpenSSL to update. Lifecycle management, so CSR generation, certificate issuance, validation, issuing CRLs, which is a certificate revocation list, OCSP, which is online certificate revocation service, and CMP, ACME, different protocols. We want to make sure it's compatible to use our tools, also be able to verify by using different libraries. Hybrid certificate, so we have successfully issued hybrid certs using X509 alternative. And we are also in the progress, we're actually about to release a new version of EJBCA that has capability to issue composite certificates. There are other form like PQC-12 dual keys that's been planned in the future. More testings with our ecosystem. So HSM's hardware secure module is definitely one of the critical integrations that we have to secure all the PKI keys. So we have done a lot of testings with our technology partners to ensure that those new algorithms can be generated in the modules, be able to do the signings and compatible with protocols and stuff. So if we put all this together, right? So we have you can do MLDSA CA, which is on the right-hand side, to generate CAs, issuing certificates. We tested it with Certbot, which is using ACME protocol, providing OCSP services, verified using OpenSSL, do the signings, the signing documents, SBOM, verified by using OpenSSL and stuff. TLS, which is also very important part of internet, right? So we're also doing a lot of testings around this. Some of the useful links, IETF hackathon, this is on GitHub, so you can actually go and check all these results using different libraries, how you're compatible with your system. So those are the informations. We also have PQC lab. So if you haven't generated your first MLDSA certificate, probably you can use this lab to set up your first post-quantum PKI and issue your first MLDSA certificates. Okay, so for the demo, I'm going to issue my first, not my first, probably I've done a lot of testings. The first, probably you've seen MLDSA certificates after the standardization publication in RFC 9881 last week. And we're going to also interact with EST protocol and issue a certs using EST automatically. We were also using OpenSSL and different libraries to cross-reference, cross-checking. And we will also do a code signing using MLDSA certificates, verifications, and then last but not least, MLDSA for TLS use case where I use Nginx and use MLDSA certificate on the Nginx and see how it works. All right. Just okay, so in my system, I actually have OpenSSL 3.5, which is the version that can support PQC algorithms. I'm going to use OpenSSL to generate MLDSA key in CSR. And I will request a certificate from my CA server using EST protocol. So this can run and I get a certificate. So we can actually go and check how the certificate looks like. So I copy this command, I'll just convert what I have received from the server. So you can actually see that the certificate has been issued. It's using MLDSA 44 algorithm, and the issuer is my PQC sub-CA. And you can, if you're aware of the size of the key, the size is actually bigger compared to our legacy RSA and ECC, of course, larger than ECC keys. The signature itself is also appears larger, which can be a significant implication when it comes to performance considerations. You know, you need to have bigger database to accommodate those bigger certificates and keys. And next, we are also going to sign something. So I have just a very simple document. It's OpenSSL Community Day Korea 2025. I use OpenSSL to do the signing. And we can actually check the CMS messages. It looks like this. We can verify it using OpenSSL. And the verification is successful. What we can also do is to use our sign server to sign this file. So first I'll make the hash. Then I'll pass the hash to sign server backend. And I will expect a signature, which is a P7S extension. So we can actually check put file dot hash P7S. So this is the signature itself. And we can use a Bouncy Castle tool called post-quantum verifier to verify this signature. Of course, in the command line, we are using a trust anchor, which we can use to verify the signature itself. So you can see this is MLDSA 44 algorithms that was configured in my sign server. How about TLS? So we can actually use OpenSSL to set up a TLS server, and we can check the communication using to check TLS 1.3 groups. You can see that the communication is actually established using MLChem 76A, which is a quantum safe algorithms. And the signature, because I have MLDSA certificate in the OpenSSL server, so it has the MLDSA signature itself. I have Nginx server. So in the Nginx server, I have two virtual server. One is using legacy legacy RSA certificate. So if you can check, the certificate is actually RSA key size 2000. But because I'm using TLS 1.3 in that server in the Nginx, so you can see that the key exchange group is actually MLCAM, which is a quantum safe algorithms. So what about if I put MLDSA in the server itself, and my Firefox actually cannot recognize and throw an error about cipher, but we can actually test this using my OpenSSL, using cur, because cur is, I can point to the OpenSSL. So I can actually run just a very simple cur command. Right, so you can see that the communication, the key type, the public key, MLDSA, you can see the results, and SSL connection is established using MLCAM. The signature is MLDSA44. Yeah, so it's coming. So PQC is here, and it's happening right now, and you can see OpenSSL is already support those algorithms. Yeah, so that's conclude my presentation today. Any questions?
As you can showed us from the Firefox example, does the quantum safe algorithm certs are not readily available at the Firefox?
The certs are generated from PKI, right? So depends on where you generate the keys. Actually, today you can use EJBCA, which is an open source version to generate MLDSA and put in your Apache server.
Yeah, Nginx or
So you can
servers.
test today, or you can use OpenSSL.
So is it readily available with the Let's Encrypt 2? Like the OpenCA Let's Encrypt or Certbot that issues certification?
I think it's on the roadmap. I'm not aware of whether Let's Encrypt supports the post-quantum algorithms. But most of, if you check the traffics from, for example, Cloudflare, they have been using MLDSA, MLCAM, sorry, not MLDSA, MLCAM, PQC, quantum safe algorithms in their traffic
Okay.
today. Yeah.
Thank you.
Anyone
Any
else?
other questions?
All right. Please give Tony a round of applause. Thank you so much, Tony.